So this project will be demonstrated on the cylinder in the demonstration period, and is particularly spectacular. So make sure you see it, along with all the other ones, of course. Over to you. F5. Get you the full screen. There you go.
Good morning. I'm Andrew, and
You need to speak up a bit.
my project is on visualizing carbon nanostructures and creating a realistic model of activated carbons. So carbon is an element. It's the sixth one on the periodic table. It's pretty amazing. It has quite a few allotropes of pure carbon that can be made, common ones being diamond and graphite that most people know. And as you also know, diamond is very hard, but it can be contrasted by graphite, which is also just pure carbon, which is also quite soft. In the last 20 or so years, more recently, researchers have managed to develop graphene nanotubes and other fluorines. And a common thing about all of these carbon allotropes or structures is that they all have order at the atomic level. They're just the same thing repeated over and over. Activated carbon, however, is classed as a disordered carbon, and it doesn't repeat over and over. This makes it a lot harder to model. And specifically with disordered carbons, we find disordered carbons that have empty spaces in them, and we call these empty spaces pores. And when a disordered carbon is like this, we get to call it a nanoporous carbon, and activated carbon is a subset of that. The pores are particularly important in activated carbon, as it leads to basically all of its applications, as the pores of the activated carbon allow it to adsorb other molecules. This adsorption lets it act as a filter or a molecular sieve, and gives it great applications in gas separation, air and water filtration, and gas storage. So to make activated carbon in a lab or something, you need to start with something that has carbon in it, obviously. And so a nutshell or woods, these are often started as your initial precursor, and then you will want to heat this up. But as most people know, when you heat up a wood, it starts to light on fire, which is not what you want. So you have to heat it in an inert environment. This lets you produce a char, and a char is one of these disordered carbons, and it has pores in it. However, when you've heated up your precursor to create the char, you generally leave things blocking the pores. This prevents it from adsorbing and removes most of the applications from it. To remove these blockages, we will activate the carbon through a process of passing a hot gas through it, such as carbon dioxide or steam. The activation also leaves behind oxygen, which can affect the properties of your activated carbon. However, my project wasn't to make activated carbons, but rather model them. So previously, there had been other attempts to model them, and starting from the first models that were quite simple, such as modeling the pore as the space between two slits in some graphene sheets. These first models were quite idealized. They're constructed by hand. They don't have any sort of predictive maths behind them to determine where all the pores should be and how big and all of that stuff. More recent models, with computational power increasing, we can do predictive simulations, but these ones completed previously were generally small, so the size of your simulation affects how big of a pore you can have inside of it. So if your simulation is too small, it limits the amount of different porosity you can find. And also, previous simulations didn't include oxygen. So my aim was to simulate these larger structure, which allows for larger pores, and also to include oxygen. So to simulate it, we employed molecular dynamics, and so molecular dynamics, we use the software LAMMPS, and this software is designed to find the most energetically stable position from atom. So if two atoms are too close together, then they're not going to be as energetically stable as if they're the right equilibrium distance. So if they're too close together, it moves one atom slightly further away, or if they're too far apart, it brings it closer. But it does this for all of the atoms, and we used over 30,000 atoms, so it was quite computationally intensive. Hence, we needed to use the capabilities of the Pore supercomputers, specifically Magnus, and That allowed us to simulate these large structures. On the left here, you can see the workflow of simulating the structure. So we started with an initial structure. We removed some atoms to simulate the burn-off. We annealed it, we added oxygen, and we ended up with an activated carbon. So the first process was to burn off the initial structure. So this is the initial structure here, and it's colored by the potential energy of each atom, shown here. So the gray atoms are quite stable, the blue ones less stable, and so on. So to simulate the burn-off, we would remove 200 atoms at a time, and we chose the 200 highest potential energy atoms as they're most likely the least stable, and therefore hopefully the ones that are most likely to get burnt off first. And then we would re-minimize the energy of the structure. To decide how to remove these atoms, and we tried different other schemes rather than just sticking with 200. And to pick these schemes, as you can tell from the structure, it's really hard to see what atoms are what and how the structure really looks like. So the HIVE cylinder was very great for visualizing this and deciding which, if it was a realistic approach to remove certain atoms, on, etc. That should be rotating, but never mind. This one is. So this is an animation of the burn-off as it progressed. So if you remember before, it started off mostly gray, but now we can see the atoms are increasing in potential energy and then changing to blue or red. This shows that the structure is decreasing in stability, and particularly this comes from the coordination fractions of the atoms. So the coordination fractions are determined by the number of atoms each atom is bonded to, essentially. So a carbon atom with only 2 bonds is called an sp atom. With 3 bonds, sp2, and 4, sp3. On the left here, you can see a graph showing the coordination fraction as the burn-off increased, and we can see that the sp fraction rises. Now, from the start, you remember that most of the carbon structures had hexagons in them. And hexagons are formed through sp2 bonding and are quite stable. However, sp bonding, which is what we see the increase in here, is less stable and more, and therefore has a higher potential energy. So after the end of the burn-off, we ended up with a structure that was quite high energy, and we would want to reduce the energy to stabilize it. And so we also simulated the annealing section. And the annealing also makes a lot of sense, as when we activate the carbon, we're passing a hot gas through it, and so it's at a high temperature. And so annealing is holding the structure at a high temperature and letting the structure rearrange itself to minimize its energy. As the annealing went on, we can see animation of it here. And if you remember before that, so this structure, first of all, was colored by coordination number instead of energy this time. So as I mentioned before, coordination number 3, which is green, is quite stable. However, we had a lot of red in the initial structure. If I can go back. Yeah, and a lot of red from the sp2 atoms, which are less stable. So as the annealing process occurred, we reincorporated these long sp chains because it only has 2 bonds, so therefore all sp atoms form into chains. And we also enlarged the pores, as can be seen here. So the red atoms decrease and we get more green atoms, being the main part. We can also see this again in the sp fraction on the left. Our sp2 percentage keeps increasing and our sp percentage decreases again. Once we'd finished annealing, the next part of the simulation was to add oxygen to finish activating the structure. So on the right here, we have the final structure with 5% of the atom's oxygen, and yeah. So, and again, it's You can see the structure, but you can't see the details of the structure. So visualization is very important to actually analyze what the structure looks like. In terms of actually how did we add the oxygen, we once again chose the highest potential energy atoms as they're the most likely to be reactive, and then we placed oxygen atoms 1.4 angstroms away. And then we reminimized the structure once again using lamps. So when we did visualize the structure, it froze.
It's supposed to be rotating, is it? No?
It's supposed to be going to the next slide.
Oh, it's locked up.
Yeah, the timer's not moving.
Okay. Interesting. Where's that?
Oh,
Oh, that's interesting. That's the one you're wanting, isn't it?
yeah, thanks. So after visualizing the structure of the oxygen added, we can find the sort of bonds that the oxygen formed to the carbon structure, how it formed, and we can classify these using terms from organic chemistry, such as ketones, epoxides, and ethers. So ketones are when you have an oxygen with a single bond to the carbon structure, as in over here. We just have an oxygen with a single bond to the structure, it counts as a ketone. When we have an oxygen with two bonds forming a triangle in the structure, we count this as an epoxide. And when we have oxygen forming part of a sort of ring in the structure, we'll count it as an ether. And then we also have peroxides when we have oxygens bonded to other oxygens. This allowed us to characterize the number of functional groups within the structure and give us a good idea of how realistic the oxygen addition went. So to actually test, well, compare with experiments as to whether our structure matched with realistically, we can look at the pore size distribution. So the number of pores and how big each of those pores are. As you can see on the left there, we have the pore size distribution in a graph. And the difference between the annealing and before and after annealing can be seen again, as the blue line shows the before annealing and it shows a very large number of small pores. But after annealing, we see that we have fewer small pores and more large pores. We can also visualize the negative space in the structure, or the pores, so to say. And here we have them on the right as the pore structures. And we have them for adding 2%, 5%, and 10% oxygen to the structure. And although their main structure looks very similar, there are some differences, such as these craters that appear as we increase the amount of oxygen. These craters are most likely caused by the fact that the oxygen is sort of poking into the negative space and reducing the size of the pore slightly. So in conclusion, we've created a realistic model of activated carbon. We've included oxygen. We've included a realistic description of pores. And to create this model, we mimicked experimental conditions by the Burnoff process and adding the oxygen with the activation. This is hopefully going to provide insight for experimentalists specifically into the atomic microstructure, and especially also the different groups of oxygen that formed. For further work, we'd like to continue exploring Burnoff methods, such as combining the annealing and Burnoff stages into one, as well as completing compression simulations, which give us more data to compare to the experimental actual physical models that exist, well, physical carbons. And also complete this process again with structures of different density rather than the 1.5 grams per centimeter cubed structure that I started with. I'd like to thank the Curtin Institute of Computation, the Curtin HIVE, specifically Michael for the MDV software we use to visualize it, my supervisor Carla, and the Curtin Carbon Group and Supercomputer Center. Thank you.
Do we have any questions from the audience?
Yes.
Ahmad. So the question is, how big is the data?
Depends on which data, but for the main structure, the files are only a couple of megabytes, I guess. But for the pore data that I showed before of the structure of the pores, those files tend to go into the gigabytes range.
Any other questions?
When you were burning off carbon, you said in an inert environment, you mean without oxygen?
Yes, so the burn-off stage, well, that's the carbonization stage to get the structure that you'd then burn off to activate. So that occurs without oxygen, but when you activate it, you'll pass in carbon dioxide or steam, which is H2O, and those both have oxygen inside of them, and that's how the oxygen ends up depositing on the structure.
And this is all by simulation. No carbon molecule has, carbon atom has died in this process. Question down the front here, Ali.
Which visualization technique have you used to show the carbon structure? Was it using VMT or VTK, OBJ?
So on a desktop computer, I'd use Oviedo to visualize it, but Oviedo, so it's an open source visualization tool. But on the Hive, I'd use Michael's MDV program, which MDV, and that lets us see it in stereo and on the full cylinder, which is very amazing.
So MDV stands for Molecular Dynamics Visualizer. Did I get that right, Michael? It's an application that was specifically developed in here in the Hive because we didn't have a way of showing molecular dynamics on the cylinder screen. Most software that you'll find anywhere really assumes a flat screen. And as you might have noticed, this one's not flat, so it causes a few limitations of using existing software. So the geometry is all wrong if you try and display images that are rendered for a flat screen on this curved screen. And it also enables us to view it in 3D. One of the aspects that you'll notice when you see the simulation is that just cover or close one eye, and you'll notice that what you could see in 3D as being nice and structured and lots of layers just becomes a mush. You just really can't tell what the individual layers are. So being able to view it in 3D is a real big advantage for this kind of data interpretation, and also being able to show it around. It just allows you to sort of be immersed in the content as well. Any other questions? Up in the back, Jonathan.
You mentioned comparing your simulation for distribution to the experimental results. How was that comparison?
That's the comparison that we're yet to do, but we have the pore size distribution, so hopefully when we get experimental data, we can compare them. Yes.
Any other questions? Gretchen.
Following on from that, how will you visualize the pore spaces from the experimental data to compare to the model data?
So experimentally, we can't visualize this sort of stuff. It's just too small, hence why we want to make models for it. But experimentalists can use certain techniques to develop pore size distributions based on amount of gases adsorbed and stuff.
So sort of jumping on from that question, usually another question that comes up is how do you visualise this kind of stuff in a written publication? So we don't have the technology currently to be able to take a Hive cylinder and compress it into a manuscript, but you can show them as stereo pairs, so you can view it either with the viewer or crossing eyes. At the demonstrations, Andrew will also show this kind of content, and it's not been developed with MDV, but another application that runs on a head-mounted display. We've got it sitting here, we've got it somewhere around, and over in the back, so it's just charging at the moment. So make sure you have a look at that as well. And that's a way of potentially providing a link in a paper for someone to download the content. Initially, you might be able to just view it on a phone, but if you have your head-mounted display, you could view it on that as well. So if there's no more questions.
Are people doing that already? Publications, can you access either 3D files or headset files?
Yeah, it's common to upload links to videos. It's not so common to upload links to 3D videos, but I think it has been done, but I'm not too sure. YouTube made it a little bit difficult by sort of breaking the 3D support a while back, a few years ago now, and they haven't fixed it yet. However, they have recently, in the last couple of years, added 3D 360 support. So the same content could be viewed on a head-mounted display as well as a smartphone or a desktop. So I think that will tend to happen more. I haven't seen any papers specifically doing it, but hopefully maybe we can do that. All right, well, please join me in thanking Andrew for his presentation. Thank you. The last presentation for the morning session is Jack McNair. He'll be presenting about his work on visualising Martian craters. His supervisor is Gretchen Benedicts, who's right here in the front. And this project is also supported by the Curtin Institute for Computation, so we again thank them for their support. All right. Right. You're all set.
Thank you. All right.
F5.
F5? Okay. All right, hello. My name is Jack. I'm a final year computing student, and my project is called Immersive Visualization of Martian Craters. Not very catchy, is it? That's better. So a bit of background first. Multiple satellites have been orbiting Mars since 1996, gathering topographic data. And when this data is presented to the public, it's usually presented in the form of a 2D color-coded topographic map. And while these maps are of great scientific utility, they're a pretty dry way of conveying some pretty interesting data, and they haven't really succeeded in capturing the public's attention. But one thing that has captured the public's attention is recent advancements in VR technology. Especially over the last few years, the Vive Pro has been released, which addressed many of the problems with the previous generation of headsets, and a whole slew of much cheaper headsets have been released for people who can't really afford to drop $1,000 on some goggles. So this was a pretty open-ended project. It only ever really had one objective, and that was take this data, make it look cool. But if I had to put that more formally, I would say that the objective was to create a framework through which topographic data could be presented in an immersive VR environment. So the target audience for the project was just the general public, school kids, basically anyone who's interested in Mars. So the data set I used was gathered by the HiRISE satellite. So that stands for High Resolution Imaging Science Experiment, and what it means is that they really wanted their acronym to spell HiRISE. So these images are extremely high resolution, about 30 centimeters per pixel at best, but usually they hover around 1 meter per pixel. And its resolution is really the reason why I chose this specific data set. One weakness is that it doesn't cover as much of the Martian surface as some other topographic data sets, but the 586 images that they do have cover terrain that is generally of scientific or geographic interest and generally looks pretty interesting too. So when I was browsing the list of DTMs, I noticed a few spots where a few of them were clustered together, and I decided that I wanted one of these spots to be the sort of centerpiece of the project. One such spot was Ritchie Crater, and so significantly large craters generally have a sort of central uplift, a peak in the middle, and that's the area that these DTMs were focused around. So when these DTMs are all merged together, you can extract a 13 by 13 kilometer area that can be explored, and this contains some pretty dramatic territory as it's the central mountain of the crater. The two other DTMs I used was this 3 kilometer diameter crater that NASA named a 3 kilometer crater, really giving their creative muscles a workout there. The reason I chose this one was because it fits almost perfectly into a Unity terrain, and the other one I chose was Casa Valles, which I used because of its, there we go. I used because of this really distinctive lava flow formation, and because of these valleys where sand is pooled at the bottom and formed some really nice flowing dunes. So how do you turn satellite data into a 3D terrain? It's actually a fair bit easier than you'd think. Unity has a kind of object in it called a terrain, and this allows you to import a raw height map and it will automatically turn that into a 3D structure. So in order to turn the satellite data into a raw height map, all you've got to do is download the GDAL, get the maximum and minimum heights of that GDAL, use these to scale it from 32-bit floats to a 16-bit PNG. The 16-bit part is important for reasons I'll get to later. You can then open that up in normal image editing software, crop it, save it as a RAW, import it to Unity, and then bam, you've got yourself a terrain. So the reason using 16-bit height maps is important is because of the limitations of the 8-bit format. An 8-bit integer can only store up to 256 different values. And when that's used as the basis for a height map, you get this nasty terracing effect, which makes the flat areas look like rice paddies and the uphill areas look like staircases. So 16-bit integers, on the other hand, have, I believe, 65,536 possible values. So you are losing some precision from the 32-bit float, but not enough to notice, and it's certainly good enough for the purposes of this project. Once you've created the terrain, I added a couple of extra touches to make it more attractive. One of them was a fog effect. This has 3 benefits. One, it conceals the edge of the terrain. Second, when terrain in Unity is far away, it's rendered at a lower level of detail, so the fog hides that. And third, even when you're in VR, your depth perception is cut off past a certain point. So when you apply a colored overlay to very distant objects, that really does help convey depth and scale. Additionally, if you add a giant particle effect spawner over the entire area and make the particles look like dust clouds, then you get an effect that looks like a nice low-key dusty breeze. You can't really see it in that picture, but I promise you it's there. So once you've created the terrains, that raises the question of how the user is going to experience them. Early prototypes for the project were in the form of Roomscale VR. But this was abandoned for a set of reasons. The main one was that it really limits your set of movement mechanics to walking around your area and teleporting. And I discovered the hard way that if you're going to be flying a very fast spaceship in VR, you really want to be sitting down. So you'd be surprised how many mechanics had to be scrapped under the justification that they will make people vomit. Some other advantages to Roomscale VR is that it's more accessible. A lot of people just don't have the room to set up a full room-scale rig. And it's easier to translate from non-VR to seated VR than it is from non-VR to room-scale VR, because you have to completely rewrite all the movement mechanics. So when you first boot up the game, this is what you're going to see. So a quick breakdown of what you're seeing here. The planet in the background is being rendered at full scale. Was it necessary for it to be that big? No, but it was necessary for it to at least be big enough that if you move your head, you get no noticeable parallax. So if you're going to make it that big, I figured might as well go the whole way. So rendering something this big does cause a few problems, mainly with the camera. If the far clipping plane is very far away from the near clipping plane, you can start to run into floating point issues. So this was addressed by using a 2-camera setup. There's one camera close to the player that captures the title card and the inside of the ship, and one much further away that captures the planet. And this sort of solution was replicated for flying around the planet as well, just in a much smaller scale. So when you hit one of those buttons there, you'll be treated to this animation. Now, I will admit this animation is a bit indulgent, but I just couldn't bring myself to truncate the sound effect. So, here's the ship. Isn't she beautiful? It is the main method of traversal around the VR environments. It's the fastest way of getting around. The reason I chose this model was because it came with a ship and a cockpit, and the big, wide, open canopy affords you a great view of the surrounding territory. So initial plans were for the craft to use a pitch roll controls, like a fighter jet. So if you wanted to do a sharp turn, you would roll into it and then pitch. But another thing I learned the hard way is when you're in VR, something you don't want to be doing a lot of is rolling. So instead, I scrapped that in favor of a pitch yaw control scheme, which is easier to use, even if it is a little bit less fun. So the spaceship generally travels pretty high up and pretty fast, which can sort of disguise the scale of the areas that you're traveling around. So eventually, you are going to want to land the ship and get out. So when you land the ship, you're going to be booted to a on-foot exploration of the surrounding area. This is good for getting your bearings and getting a sense of the scale of the areas that you're exploring, but it's too slow to really enable much exploration, which necessitates a ground vehicle. So the original plans for this vehicle were for it to be a sort of Martian rover. But the problem with that idea is that Martian rovers have wheels, and some of the terrain you're exploring is very bumpy. And bumpy terrain mixed with a vehicle with wheels is a recipe for ruining the Hive's nice carpets. So instead, I switched that out for a hovercraft. So in this case, the force that keeps the hovercraft aloft can act as a sort of smoothing mechanic that keeps the hovercraft flying straight when you're moving over bumpy terrain. At least that was the theory. In practice, you get a sort of catch-22, where if the hover force is too high, you'll stick too tightly to the terrain, and it'll still be bumpy. If it's too low, you'll move more smoothly, and it'll be more comfortable, but as soon as you try to fly uphill, you'll end up crashing into the ground. So the solution to this was to, rather than applying the physics to the hovercraft itself, apply it to a point in front of the hovercraft. So this point sticks pretty closely to the topography of the ground, and the hovercraft that you're actually riding follows it on a sort of elastic band using a smoothing algorithm. And the effect of this is that it makes the hovercraft much smoother, and it also gives it a sense of weight and momentum that it didn't have before, making it, in my opinion, a fair bit more fun to drive. So, I have a few ideas for directions this project could be taken in the future. One of them, my priority for creating the project was laying down the basic mechanics for exploring these areas, rather than creating lots of maps. But now that the mechanics have been laid down, it's certainly possible that given a few weeks of work, someone could add tens, if not hundreds, of maps to the program. Alternatively, you could go in the other direction, go for quantity instead of quality. So far, the maps just have a single texture repeated on top of them, but if you were to get someone more artistically inclined than myself, then with a bit of time and skill, they would be able to get those maps looking really nice indeed. And third, at the moment, all you can really do in these terrains is explore them, look around, get a sense of the topography. But if someone were to add, for example, some kind of scavenger hunt or a checkpoint race, or some kind of gameplay mechanics, it might make the simulation more engaging. So, a few people I have to thank. First, my supervisor, Gretchen. She's been an absolute joy to work with. Also, the people at the Hive. I have to thank Andrew and Susanna for keeping us all on track, and Michael and Wes, without whose technical expertise this project wouldn't have been possible. So, that's the end of my presentation. Any questions?
Any questions? Jonathan?
How do you need to use Mola to create like distant terrain, horizon?
Okay, that wouldn't be too distant. It would raise some questions about too difficult, sorry. It would raise some questions about GPU usage, but it would certainly be possible to use these molar DEMs to create a much wider terrain and layer the more detailed one on top of it. One reason that I didn't do this is that the molar DEMs use a sort of a different map projection than the high-rise one, so it would require a little bit of fiddling, but it is certainly possible.
Any other questions?
Tough crowd.
That's not one observation, I suppose, is that, you start to say, well, you want something that's thrilling for the casual viewer. I'm finding that the more I see of 3D reconstructions, even things that I thought I knew well, I didn't know at all. And what our concept, say, academics concept, oh, well, I can imagine it without this visualization. I don't think it's really true that each person sees it in a different way in their head. And so even the experts, I'm sure, finding this sort of thing quite liberating and exciting.
In fact, that was the inspiration for the project. Is Gretchen wanted to see it with her own eyes, like she was on the planet. So that's the motivation, because you do. I mean, that's one of the aspects of visualization. You gain insights which you might not gain through other means. Stephanie.
Are you convinced, or how convinced are you, how confident are you that you have reduced this potential for motion sickness? What level are you at with that?
Okay, I've used it myself and not felt much motion sickness, but for the most part, that's what you guys are here for. It is, I have noticed that I am perhaps a little bit more resistant to motion sickness than the average person, so I'm not quite sure.
As you're working on this project, did your tolerance to that motion sickness change? Did working in VR make you more resistant?
I have heard of people sort of developing VR legs, but no, not really. I've kept the same resistance to motion sickness throughout, so it might, I assume it's partially acclimatization and partially just a sort of inborn resistance.
Question over here.
It's interesting that you've chosen space, for your VR. Have you ever explored any other content areas as well within that, or does space apply itself very well?
No.
Repeat the question.
I'll repeat the question.
Oh, no, sorry. Well, the microphone can't pick you up.
So what she asked is if I've ever worked with VR in any other contexts, which is an easy question. No. This is the first time I've ever worked with VR or game development in general. So mostly I'm just a computer scientist, so I'm working with the back end typically.
Any other questions? If not, well, thank you very much, Jack.
Thank you.
So at this point, we'll break for 10 or 15 minutes, let the students set up their demonstrations around the room. So Jack will be in the back here with the Vive Pro head-mounted display. Oh, okay, over here. It is over there, okay. It's in both. So the head-mounted display will be over here, and you'll be able to see what the person wearing a head-mounted display is seeing on the wedge screens behind. We've also got another version of Jack's simulation running on the dome display. In fact, there it is right now. On the display just over here, we'll have Lauren's presentation, or sort of a reinterpretation of Lauren's presentation, some more data sets. Just a reminder, she's had to head off because there's a conference in the city today. I expect Chris is probably heading off there very shortly. On the cylinder display will be Andrew Thomas's carbon nanostructures. Encourage you to see that. And on the two halves of the tile display, we'll have Isaac and Erin's project shown up here. So I encourage you to take a little walk, come back and see all of the projects demonstrated, and we'll be restarting presentations again at 1 o'clock. So enjoy your lunch, enjoy the demonstrations, and see you back here at 1.